Hello everyone, my name is Ahmed Al-Khadir. Today I will present our paper ASID, which stands for Accessible Secure Unique Identification File, ASD File Security in Next Generation Blockchains. My email is provided for any question about this paper. And today I will cover the following points. I will introduce the blockchain technology and how it could be used in CBS and IoT environment. Afterwards, I will talk about recent distributed technology, including multi-chain technology, our previous work. The rest of the points are related to the proposed paper. First, I'll briefly explain the method and talk about the novel contributions of this paper. Third, I will explain the whole technology we are proposing in details, including the components and the operation. Finally, I will illustrate the result and compare our work to previous work related to this area. Here in this slide, I will explain IoT and CBS since we are targeting these two environments. IoT is the interconnection between multiple heterogeneous systems. These systems are able to connect to the internet and also able to exchange and share data through the cloud. This cloud will do some analysis and give some decision and feedback based on the information or based on the input. CBS, and here we see the difference between the CBS and IoT. CBS is an IoT environment integrated with actuator that could control and make physical changes according to decision and feedbacks. Sorry. Looking at the definitions and comparing them to our daily services, the contributions of applying CBS and IoT will improve the performance, the overall performance of the systems. The entire productivity of the system will be much better. However, the network is not limited to a certain number of devices. The number of participants could reach billions of things and systems. Keeping the system's interaction, analysis, storage, and security in a robust state will be a challenge through a central authority. And some of the challenges that we might face are the latency, power consumption, security, scalability, and the accuracy of the system. For these challenges, several solutions have been proposed, such as parallel operation, decentralization, fog computing, and the last one is the blockchain technology. All of them are fulfilled somehow in the blockchain technology, and that's what brought the idea of working on the blockchain technology to see the contribution of this technology to the CBS and IoT environment. Now, I would like to start to explain the blockchain technology. What is the blockchain technology? In 2009, Bitcoin, the first and the most popular cryptocurrency in the market, has been launched. This cryptocurrency uses the blockchain technology to perform its transaction and operations. Now, what is the blockchain technology? Blockchain technology is a distributed ledger, as shown here in the graph, is a distributed ledger that uses a linked list graph for a group of digital assets, and each group is represented as a block. The linked list of the transactions are organized in a public ledger published by regular user traders, let's call them traders, and validated by miners. The order of the new transactions joining the ledger should be preserved, as we see that each block is related to the block previous. We can't add a new block instead of an old one. Should be placed in a public ledger under two conditions. Honest publisher, the publisher of the A block should be or should have a valid address, a valid digital signature, and consistent order. That means we cannot add, as I said, we cannot add a block, old block, to instead of a new one. We just have to keep the order of the graph. Last thing about the blockchain technology, the blockchain technology deploys a consensus algorithm to validate a group of transactions. Consensus algorithms such as proof of work and proof of stake. Now, we understand that the blockchain might be a solution for CBS and IoT challenges, but the blockchain technology itself has its own limitations. I have here mentioned some of the limitations, like the high energy consumption, which is a main one, lack of scalability, another one, high latency, lack of privacy, limited one-chain storage capability, and fake block generation. These challenges, most of them comes from the consensus algorithm, like the high energy consumption. It's a challenge comes from the consensus algorithm. Lack of scalability is the structure of the linked list of the technology. High latency also comes from the consensus algorithm. And we can go on and see the main issue here, or the challenge, is the consensus algorithm and the structure. All of them are related whether to consensus algorithm or the structure of the linked list. Storage and process power and time consumption are directly related or have a direct relationship with the ledger expansion. Thus, the fees and operational costs will increase significantly. And here our discussion is all about a device that have an adequate capabilities to perform some operation. But what about the devices with limited capabilities, such as the device we are using in CBS and IoT? The issue for sure will be a bigger issue here. Now we know that after the blockchain technology, we have there has been many technology introduced after the blockchain technology, such as the Tangle technology and hash graph technology. This technology has been introduced to resolve some of the issues in the blockchain technology. And as I mentioned in my outline, our previous work is also proposed to resolve some of the problems in the blockchain technology and the recent other technologies. Since the technologies introduced after the blockchain all targeting the financial sector, not the CBS and IoT, or mainly for the financial sector. So we here have Tangle technology. Tangle technology is a distributed ledger using the linked transaction. Each transaction is linked to two previous transactions based on the selection method, and each transaction is doing the or performing the proof of work to validate the previous two transactions as a work to be appended to the network. And hash graph technology, here we see that we are using hash graph technology, and this technology using the BFT or the main BFT consensus algorithm, and using the gossip protocol, and build the network based on that. See how they are reaching agreement using the gossip about gossip protocol. And here in our previous work, the multi-chain technology. Here in multi-chain technology, we are integrating multiple blockchains in one multi-chain which give the flexibility of the network to use one blockchain for a purpose and another for another purpose. Moving forward, here I would like to, before I start to explain the method we are targeting today or talking about today, I would like to explain this important slide that illustrates the framework of the technology, of the multi-chain technology, and show the flexibility of identifying a certain blockchain for a specific purpose without interrupting the whole network. First, at the left side of this framework, we have the nodes registration process through an independent ledger which represents the virtual existence of the actual nodes within the network for security and integrity purposes. And from this independent ledger, we extract the secure identification file in the network. Second, at the right side of the slide, multi-chain is represented in organized shape for explanation purposes. The first thing we should know here is that there is a genesis block generated while initializing the network, which is the backup node, the first block. Any new node will be added, will form the genesis blockchain, which is the yellow part here of the network, and the rest of the network will be built on that. So that shows the framework of the multi-chain technology using the node chain method to build up the multi-chain technology. In this slide, I'll give a brief explanation about the proposed paper. First, this paper targets the integrity and security. That's the main target for this paper or for this method. The method is basically creating a linked list, as shown here in the figure, a linked list of nodes using the conventional linked list of the blockchain technology, as shown in the figure here, with a different consensus algorithm and different block structure. We will go over the consensus and the data structure or the linked list structure. This method is designed mainly to the multi-chain technology, our previous work. However, it could be used as a supportive independent ledger for registration and authentication. Many components within this method, for example, let's see extrinsic parameter is one of the components. Extrinsic parameter is the manufacturer specification of each node that's going to be extracted to be added to the block as a virtual existence of the same node. Registration algorithm is an algorithm that reach an agreement of adding a new device. Node chain is a chain we have here. Request, responses, and unique identification generator, which is the function responsible for generating the UID for each device, and this function just can be just in the backup node. In this slide, I have covered the novel contribution of the method, which is, to the best of our knowledge, it's the first method that creates digital identity assigned to each node using the blockchain technology, and it's the best to our knowledge that it's the first protocol that uses the specification of nodes manufacturer parameter to create a virtual node within the network to monitor the nodes and assure their integrity through a series of linked list nodes. Here, I will go and talk about briefly about some of the components. For example, the node chain. Node chain here, as shown in the figure, is a series of linked UID that have been generated using the target hash of extrinsic parameter and rehashed with the previous UID. We can see here the UID are linked in addition to the header. And if it's clear that the UID here, it's actually the miracle tree. The miracle tree of the extrinsic parameter in addition to the previous one. That's what creates the UID of the node. Here the requests, we have two requests, two transactions are generated from the device that wanted to join the network. First, the transaction of the extrinsic parameter, as shown here in the container on the figure on the right, The second one is the public constructed ID. All of them are sent to the network, broadcast to the network. And what are the extrinsic parameters we can look for? It's not a fixed type of parameter we're looking for, but we are looking for something that represents the actual device within the network. For example, the buff signature, it's a main one. Location parameter, MAC address, IP address, public ID, firmware parameter, SRAM, buff signature, process power, or CPU parameters. So all these parameters will be used as a parameter within the extrinsic part to be hashed and create the UID. For example, not all of them need the location. Not all the application need the location. So we don't have to add the location. Here just some examples. I use the buff and MAC address for my implementation, but the rest can be added based on the application targeted. Now I will talk about the unique identification generator. It's the function that can be found in the backup node, and it's responsible for generating the UID. UIDG is a function exists only in BN, and the function used to generate the UID for each node, and it includes two modules. The first one is script, the second one is SHA-256. To understand more, the script function is already exists function, and this function used in Litecoin, I believe, and we added the SHA-256 to give one hash fit to the script function, because the script function has its own parameters that make the function hard to attack. For example, we have HMAC here is a cryptographic function. BBKDF2 is a password-based key derivative function. It uses the HMAC value from the value and add sort to it and apply some number of iterations. Then it fed the SMIX, which is an algorithm uses a certain number of iterations based on the parallelization factor here defined in the script function. This algorithm uses all the memory allocation for its operation to make any attack very expensive, and the result of the SMIX is going to be fed to the second round of the PPKDF2 as a salt, and then we will generate the UID for the device. Now here I would like to show the differences between the differences in the block structure between the blockchain, the conventional one, and the node chain. Here we have in the left, we have the blockchain technology. We have the conventional structure of it, the block header, source ID, content, and timestamp. And the block header contains the header of the previous block, miracle tree, and timestamp. On the right of this slide, we have the node chain block structure. We see that we have two hash places. We have the node UID of previous node, and the miracle tree of the container, and we have the header here, which is similar to the conventional one. In addition, the rest of it are all similar, but the difference here, we have two hashes, and this is the virtual node header, not the block header, and here we have the UID, not the content or the collected transaction. Moving forward to the operations of the node chain, here we have two types of nodes, the regular node and the backup node. Now we have one node within the network, which is the backup node, the one initialized with the system, and we would like to add one new node. So what's going to happen here? The first thing, the node will extract the desired extrinsic, then hash it, sign using module public key. Module public key here I mean the TPM, because we are not registering the nodes, the new node with the digital signature within the node, but we are registering this node with the TPM, so it can build its own digital signature while doing the process. Broadcast the container, which is the transaction number one, which is the extrinsic parameters. Then construct a new public ID from a private ID. Then sign using module public key and broadcast public key. So we have two transactions, one for the parameters and the other one for the public ID. Now the only node that have the trusted module public ID predefined to the system is the backup node. So the backup node will receive the transaction, authenticate the source by comparing the public key with the predefined public key, claims the transaction, create the UID using the UID generator, identify the new constructed public ID using the UIDG function here as it shown here in the figure. Now the third step, the backup node will create the block and add the UID, public ID, and assign timestamp, then we'll broadcast it to the network and update the ledger. This is how we add a virtual node content to the node chain. Now moving forward, since we all understood or went over the operation of the method, now I would like to show some result about our work. Here in this implementation, we use Python to create our B2B connection and build the protocol. Also, we use PostgreSQL database to store the blocks or the virtual devices. And for the time analysis, we use 3 scenarios, 5, 10, and 15 nodes, which we're trying to make the registration step for 5, 10, and 15. Now for 5 nodes, we see here that the total registration is 21.9 millisecond. The minimum was 2.2 and the maximum was 5.7, but the whole registration process was 21.9 for 5 nodes. For 10 nodes, we have here a total registration of 46.4. Minimum is 2.2 and the max was 7.3, but here we see like it's more than the double of the 5 nodes. Now let's see the third scenario, which is the 15 nodes. We have a total registration of 63.1, 1.4 minimum and 6.6 max for the whole 15 devices. So as we see here, the total registration number is increasing with the increasing of the number of devices, which is might reach at some point to minute or 2 minutes if we're talking about 500 devices or more. The whole registration process, which is a good time, shows some fast response. Now here in this slide, I'm comparing the 3 scenarios, and the differences here, as I said, we see that the direct relationship between the number of the nodes and the total registration time here. The last slide here related to the result here is I'm trying here to compare our work to other previous work. For example, the proof of authenticity, here we have a predefined manufacturer, predefined global blockchain. That means they have a global blockchain for all the users and a local verification for one-time build. The rules of the miners here is the registration and the authentication, and they're using the conventional way of the blockchain. The second example here we covered is the proof of authentication. It's also a manual pre-identification and using the trusted node verification, and the purpose here is only for authentication, and they're using the blockchain conventional linked list. Proof of buff enabled authentication, manual pre-buff signature identification. Also, there is a miner or trusted node verification, and it's used for authentication. Also, the same linked list. Proof of block and trade. Manual pre-identification and admin verification that used for registration and authentication, both for the registration of the devices and the authentication. That's why it's called the block and trade. And here the linked list is the conventional one. MC-BORA, our previous work, MC-BORA, which is multi-chain for proof of rapid authentication. We have a manual pre-identification for a file that holds the UID for all the users and distributed over the all users. We don't have role-solved minor. It's fully decentralized for our previous work, and multi-chain we're using the linked list multi-chain. Now for the current paper, here we don't have a pre-identification for the same device. We are a pre-identification for the trusted modules and a local backup nodes for ID construction and registration. The distributed authority, after we do the registration, the authority of the system will be distributed over all the users, since we are using or extracting the node chain to one file distributed over all the network. And this node chain is just used for registration process, not used for the authentication, just for registration step, and for the authentication part, which is going to be our future work. And it's used the linked list of blockchain and multi-chain. Now here, to conclude my presentation for today, first I briefly explained IoT and CBS and the contribution of them and the challenges of the IoT and CBS, and also talked about the blockchain technology and how it was been proposed as a solution to the challenges of the IoT and CBS. And we understood the problem of the blockchain, the problems or the challenges of the blockchains and where it's related to which part, and that's what brought the idea of enhancing this part to apply this technology, this useful technology, to the CBS and IoT with the limited capabilities devices. Then I want to explain the distributed ledger technologies, recent one like the Tangle hash graph or Hedera hash graph. Then I explained the framework of multi-chain technology, adding the node chain technology as a part of it to show the flexibility of this multi-chain technology. Then I went and explained ASID, our work, our method today, and the contribution of ASID. And for our future work, we are intending to work on the registration process and the authentication process within the multi-chain technology and to create a real case for our future work. And here the references of our work. This is number one is the reference for our previous work, and here it's some of the important references we are used here today and in the paper in general. Last thing is an acknowledgement. We all would like to acknowledge financial support from the Saudi Arabian Culture Mission. Thank you all for listening and attention, and I would be happy to answer any question. Thank you all.